Particles and waves, differentiating characteristics. To classify and consider a physical element as a particle or a wave, we should first know and have established some essential characteristics of these elements, because otherwise we could include other elements that have nothing in common with them. And that is what often happens in reality. We sometimes say that a particle is a wave, or that a wave is a particle, that sometimes a particle behaves like a wave, or simply that an element is both a wave and a particle, and all this because we don't know how to distinguish them, nor have we established the properties that each must have. From the physical point of view of their properties, particles and waves are completely different, which can be clearly seen in the attached drawings or diagrams. Particles. 1. A particle is a material physical body of minute dimensions and with a great capacity for movement and displacement without deteriorating. A particle consists of a tiny amount of cosmic energy condensed into matter by the action of gravity. It has infinitesimal dimensions, depending on the amount of matter it contains, although it also possesses a gravitational field that is also small, depending on the particle's size. By applying energy or force, a particle can move more or less freely, acquiring a certain amount of kinetic energy depending on its velocity, and retaining this kinetic energy almost indefinitely if it encounters no obstacles, brakes, or friction to diminish it. Let's recall the principle of inertia, or Newton's first law, which states that everybody remains in its state of rest or uniform motion in a straight line, constant velocity, unless acted upon by a net external force. This is the principle followed by particles. In other words, a particle is a very small piece of matter with great ease of movement, capable of carrying applied kinetic energy and transmitting it to other particles through collisions, friction, etc. To give you an idea, and referring to subatomic particles, their dimensions can range from an infinitesimal volume to 10⁻⁻30 cubic meters, allowing at least 10⁻26 particles per cubic meter with some flexibility in volume and movement. Conversely, according to the considerations of the slit experiment, if the particles were waves, they would each occupy more than 1 cubic meter, making it impossible to detect and measure each one individually in a field composed of those 10⁻26 waves. In other words, a particle is a very small piece of matter with great ease of movement, capable of carrying applied kinetic energy and transmitting it to other particles through collisions, friction, etc. To give you an idea, and referring to subatomic particles, their dimensions can range from an infinitesimal volume to 10⁻⁻30 cubic meters. Waves. 2. A wave is something entirely different. It is the oscillation of a large field or fluid, which, without having a displacement motion as a whole, can transmit kinetic energy through this oscillation, that is, through the thrust between the oscillating molecules of the fluid medium. But note, there must be a field or fluid that oscillates. A vacuum cannot oscillate to transmit oscillation or thrust energy. That is to say, a particle, which is of minimal dimensions, can transmit kinetic energy through its own motion produced by an applied initial force, whereas the wave or oscillation occurs within a large field or fluid, which does not move and only transmits kinetic energy through this oscillating motion and thrust. But this oscillation in the fluid produces a movement and deformation of the equilibrium state of the fluid molecules with a significant expenditure of energy in this deformation, eventually exhausting all this applied energy or force if it is not further applied. Therefore, particles and waves are completely different and their qualities cannot be interchanged or confused. Particles are of relatively small dimensions, move easily and freely, and are capable of easily transporting kinetic energy, etc. Therefore, due to their small size, millions of particles can coexist in a very small space without interfering with each other. Waves, on the other hand, are produced in fields and fluids of relatively large dimensions, which are difficult to conduct kinetic energy through and require energy expenditure when this energy transmission occurs through oscillation. Therefore, expansive waves of relatively large dimensions cannot coexist in a small space without interfering, cancelling each other out, being measurable, etc. For example, consider a puddle or lake on which it is raining and multiple drops are falling simultaneously. with a good observation instrument, we can measure the number of drops, water particles, that are falling. But we cannot measure the extent and development of each of the waves produced in the water because they would all interfere, add up, deflect, cancel each other out, etc., forming a mixture, noise, of waves impossible to measure and track individually. Now imagine this multiplied by trillions of times. What would happen if, in a cubic meter, all the particles there were all behaved as waves and added up and interfered with each other? Do quantum waves exist? Having analyzed, albeit briefly, the difference between particles and waves, we can ask a question: can particles and waves really be confused, assimilated, interchanged, etc., and can we conclude that particles sometimes behave like particles, sometimes like waves, and sometimes are both particles and waves? Well, it seems not. It's not possible. So what has happened in quantum mechanics that has unified these two very different physical concepts? In my opinion, which may not be correct, it has all been a transfer of physical reality into the mathematical imagination of modern scientists. We forget about physical properties and characteristics and unify them imaginatively through certain systems of our mathematical formulas. Therefore, and with all due respect to quantum physicists, whose work I respect, I understand that quantum mechanics has a lot of imagination and very little reality. Friends, I've added a diagram to the explanations of waves and particles, which helps to understand that particles such as photons, electrons, and other radiation are, in essence, particles. That said, we can think of them as waves and measure their energy as such using Planck's formulas. Instead of measuring them as particles, 2E equals m.v powered 2, we can measure them as waves, equals h.f. However, they remain particles in simple linear kinetic motion, without an oscillation frequency, which they couldn't have, since that would represent a continuous expenditure of energy for that oscillation.